Irina? No. I think this is an internet problem. I mean, I wish Elon Musk or Bill Gates could do something about this.
Hello.
Yes.
Yeah. Okay. This is Akeju. So, I don't know. I said though I'm supposed to come up by 15:30. So, but I think all the speakers are not ready to speak because of the slides. So, but I'm ready.
No.
I
think your time is your time is in the afternoon, UK time. So I think you should wait.
Okay.
You should wait for your presentation.
Okay, because I'm.
Okay. I'm just waiting for Irina if she can speak. It seems she has internet problems. But in the meantime, I think Tolu is from the US. Well, she's currently in the US, so she can speak.
Hello.
Hello, Irina. Are you there?
Yes.
Are you able to give a talk to us right now?
Yes. Can I share my screen or you share the slides that I sent?
I haven't received your slides, Irina. I don't think I received your slides. When did you send them right now or a few minutes ago?
Yes.
I haven't received them, Irina. I don't know why, but I haven't received it.
Can you see my screen?
Yes, Irina. Yes.
Okay.
All right. Can you begin your presentation? So this is Irina from Makerere University in Kampala, Uganda. She's gonna speak about prediction of stock prices in multiple markets.
Yeah, I'm going to talk about predicting stock prices in multiple markets with the exponential Einstein-Lindbergh and the geometric Brownian motion models. So this is the outline of my presentation. We are writing a paper with Dr. Ini from Nigeria, and I have the motivation, stochastic models for stock price prediction, literature review, methodology, results, and finally the conclusion. So I'm going to predict stock price. We are going to use the exponential Einstein-Lindbergh model and the geometric Brownian motion model to predict stock prices at the Uganda Securities Exchange as well as the Nigerian Stock Exchange. So investors at both the Uganda Securities Exchange and the Nigerian Stock Exchange need to know when to invest their capital in order to maximize returns and of course reduce losses. So the stock prices are, however, are volatile. They move up and down, and that makes it difficult for investors to decide when to buy, sell, and maintain a stock at any of the exchanges. However, in doing so, there is need to identify a suitable model to be used for each stock at a particular stock exchange. So the objective of our study is to use the exponential Einstein-Lindbergh model and the geometric Brownian motion models to predict stock prices at the Uganda Securities Exchange and the Nigerian Stock Exchange. These are some of the stochastic models that are used for stock price prediction. We have the geometric Brownian motion model, abbreviated as a GBM, the Einstein-Lindbergh, the Cox-Ingersoll, the exponential Einstein-Lindbergh model, and these three are mean reverting models. We are going to use, for us in our paper, we are going to use the exponentials and Lindbergh model, that this, and then the GBA model for stock price prediction at these two exchanges, that stock exchanges that I told you earlier. For the case of Uganda, the case study is going to be on Stanbic Bank Uganda, abbreviated as SBU. And for Nigeria, it is going to be on, the case study is going to be on Stanbic IBTC Holdings, abbreviated as Stanbic.
Okay.
Hello, I can't hear you. It is raining heavily.
It's okay.
Can I proceed?
Yes, please proceed. Yeah, please,
Okay.
please proceed.
So we chose these two models because of their positivity. They always give positive values for stock prices during the stock price prediction, and this is because of the exponential term in their solutions. And another thing is that the exponential Einstein-Lindbergh model is more adherent to economic reality, and it reconciles more of the properties of Brownian motion parts with physical reality. So this is some of the literature review that we used. These two people used geometric Brownian motion to forecast or predict future closing prices of small sized companies, and their results were accurate with the GBM. This person, Major Vega, in 2018 modeled the spot prices of gold using the exponential and Lindbergh model, and the results were also positive. They were in line with the actual stock prices. These people, Kasozi and other people, in 2023 predicted the stock prices. Actually, this was at the Uganda Securities Exchange using the exponential and Lindbergh model, and the results were also in line were close to the actual stock prices, and the the mean absolute percentage error for this model showed a good forecast. This person also used GBM to predict stock prices at the New York Stock Exchange, and GBM still provided accurate predictions. We used, it was lemma to solve the two models, and these were the solutions that we used. This was a closed form solution, and this wasn't. So we used the discretized form of the exponential closed form solution. Then estimator that we used to estimate the parameters the of each of the models. For the exponential Steinlenbach model, there were three parameters: the mean reverting speed, the long run mean, and the volatility. And then for the GBM model, we had two parameters: volatility term. Then later we computed the MAP, mean absolute percentage error, and then we used it to compare the forecasting accuracy of the two models. The data was obtained from the Wall Street Journal for each of the stocks from each of the stock exchanges, and this was the set of data that was used to obtain the parameters for the case of SBU at the Uganda Securities Exchange. Then this set of data was used to obtain parameters for the case of Stanbic at the Nigeria Stock Exchange. These are the results that we obtained. For the parameters of the exponential OU, for the case of Uganda, these were the parameters. All of them were positive, and they were used to predict for 100 days before the outbreak of COVID-19. Then for the case of Nigeria, these were the parameters that we obtained. The mean reverting speed was negative and the rest were positive. For the MAP values, for the case of Uganda, using the parameters for the exponential onset and then back model, while predicting the mean absolute percentage error for the 100 days that we used was 7.98. I just forgot to round off. So this was a good forecast. And then for the one of Nigeria was too big. The forecast wasn't accurate. These are the simulations that we had. This is showing the actual and predicted prices of Stanbic Bank Uganda at USE using the exponential onset and then back model. And this one is for the one of Nigeria. It had an exponential, it was exponentially growing. Those were the results while using the exponential OU. Then for the GBM model, for the case of Uganda, these were the parameters. I just forgot to round off, the values are too many. These were the parameters, and the mean absolute percentage error that we got when we predicted for 100 days still before COVID-19 was 9.63, and it was a good forecast. And for the case of Nigeria, these were the parameters for the geometric Brownian motion model, and the mean absolute percentage error for 100 days that we used to predict before COVID-19 was this, and the MAP value was smaller than the one for Uganda. So the GBM showed better results for Stanbic in Nigeria compared to the one in Uganda. And these were the simulations from the GBM. This is the one for Uganda, and this is the one for Nigeria. So finally, we have the conclusion from the two predictions. All the parameters for the exponential OU were positive for the case of Stanbic Bank Uganda, while for Stanbic Bank at Nigeria, one of the parameters, that was the mean reverting speed, was negative. So we concluded that there was mean reversion in SBU data while it never existed in Stanbic's data. This is Stanbic at Nigeria Stock Exchange. These were the absolute errors as we have previously seen. And finally, the exponential OU is concluded that it performed better with SBU data compared to Stanbic's data at Nigeria. And the significance of the study includes, and it's not limited to this, advancement in academic knowledge in financial modeling, and the use of the two models in the analysis will help to manage risks and increase transparency in the financial markets. The predictions will provide valuable insights to business leaders and policymakers, will be used during allocation of assets and questions about market efficiency and to reduce investment risks, hence maximization of returns. These are some of the
Thank you.
results.
Thank you,
Thank you for your attention.
Yeah, thank you, Irina, for your talk, for your wonderful talk. I really appreciate everything that you're doing, in spite of all the difficulties that you have, difficulties with internet, etc., in your country. I think we don't have time for questions now because we are running out of time. One of the speakers did not attend. So let's go to the next seminar presentation by Doku from the University of Ghana. Doc, Doku, can you hear us?
Yes, I can hear you, please.
Can you please share your slides and yeah. Irina, can you please close your slides so that thank you. So Doku is going to talk about estimation of the tail index of Pareto type distributions using a dependent random weights regularization. Sorry about my English, but that's the so. Thank you, Doku, for your time and your presentation.
Please, can you see my slides?
Yes, I can.
Okay. Thank you very much for giving me this opportunity. My name is Dukwan Ponsa, and my presentation is going to be on estimation of the tail index of Pareto type distribution using dependent random weight regularization. And I wish to say that this is a joint work with my PhD student, Dr. Okran, my master students, Setanfu, and two other MSc students, Ajay and then Apia. The main objective, my main outline will be, I'll talk about the introduction, objective, methodology, application, and then conclusion. There is no simulation study here, and I wish to say that simulation study can be done to confirm some of our results. Now, extreme event used in the broad sense captures both occurrence of unexpected values and exceedance of a particular threshold. And extreme value theory models extreme events. Now, our main aim sometimes is to estimate, is the estimation of the value of the extreme index in the extreme value theory. Now, various approaches have been proposed in the past. We have the block method, where you divide the data into blocks and then you pick maybe the maximums or the minimums of the blocks as an estimate. And that one has a lot of challenges. Then the others also proposed the peak over threshold method, where you set a threshold and any data point beyond the threshold is used as an estimate of the extreme value index. This also has some challenges because even setting the threshold is very difficult for in practice. So. Now, others like the Brilliant and then Britandy have proposed the case where you use the K top order statistics. So if you order your data, then you use the K top order statistics as an estimate to do the estimation of the state index. My goal in this presentation is to propose an estimator which is a reduced bias one, and one it's asymptotically unbiased, it's asymptotically consistent, asymptotically normal with minimal variance of the Hale estimator. In fact, Hale has the minimal variance when it comes to the estimation of the tail index in this category. And then application-wise, it might show some efficiency with the stability of the EVI estimate against the number of top order statistics. Now, the Pareto type distribution is a distribution with tail index exhibiting this kind of properties, where it is growing slowly. It's a slowly varying function at infinity, and it satisfies this property here, 1, 2, and the same property can be rewritten in the form of the quantas, and for the quantas it is represented by the 3. And in fact, there is a relationship between the quanta version, quanta formula, and then the previous one, and it's indicated by that. I mean, the CDF itself or the T index. Now, the main assumption is we are going to use here is usually the second order assumption, and it states that there is a real number we are calling the rho, and a rate function B satisfying the following properties. 4. Yes, the log of the LXU over LU. You take the limit, it approaches some rate BT times HU. And this was done by Bieland and Ter in 1999. Now, the regression-based approach. In fact, the Bieland, we know that our, what we call it, if you order the data, and we can represent it as ZJ, where the Xi are the top, the order statistics. Sorry. Now, Bieland proved in their paper, Bieland et al., 1999, that we can approximate the Z by a regression line, or by this formula here, or a regression line in this form, in which the random variable here has to do with the FJs, and they are exponentially distributed with mean one variance, mean one, sorry. Now, the constant here is represented by this. You know, the B was introduced in the definition of, in our, say, our assumption number 4. It's the same B here. Now, so again, in 2002, Bieland in fact shows that the weighted log spacing Z, you know, the Z represented as the top order in terms of the top order statistics here, can be written as a regression, or can be approximated by a regression model, where the regression constant is the gamma, which is the T index, and then the constant is the Bn, and then the Cj is represented by the, it's a function of the log spacing. Okay. So the slope is the B and is given by that. And the error term in this is, again, is their IID, or they are independent, sorry, and asymptotically, it has a mean 0, and then the variant gamma square. As you know, as n goes to infinity, the k top, the k also go into infinity, because it represents the top, the k number, k top order statistics, sorry. And there is a requirement that the ratio of the k and the n should go to 0. So the k is not too large, though it is large, it's not too large, so that if you divide by the number of the data points, it must go to 0. Now, the regularized weighted least square that we seem to propose will have some weights. So it's like we are going to do a least square, but we introduce some form of weight. And if you look at the weights here, what is involved in the theta aspect, what is in the bracket, you could see that it's a decreasing function. And then also we multiply by a kernel. Depending on your choice of kernel, you can control how the T index will behave. Now, the assumption on the kernel, we assume that the kernel is, if you integrate it over the possible values of 0 and 1, it is finite. In fact, going forward, you see that we are going to use the one that integrates to 1. That is probability kernels. And then the theta here, we are also assuming they are independent and uniformly distributed. What the theta is doing here is that we know that the function in the bracket is decreasing, but we want to control how it is decreasing. It should not be too fast in such a way that you throw away most of the data. So we want to throw away the data, but we throw it away gradually, not in a haste. We throw it away gradually. Then also we introduce this alpha k here. Yeah, the alpha k again helps us to be able to establish our convergence. I mean, the asymptotic distribution of our estimators. So again, for the conditions on the theta, the alpha is that the alpha should be going to infinity of order a constant times k. Now, if you introduce our weight in the loss function, then we're going to have a loss function. And if you see this part here, we are weighting this part by the WJ, and also the penalty term here. There's a penalty term here, and the penalty is also being multiplied by the sum of the weight. Now, we want to say that the sum of the weight is not necessarily a constant, because if you look at the weight, they are random in nature. So if we sum it, we are also getting something random. Now, the beauty of it is that because of the conditions that we place on the theta, we are able to estimate it with a probability one, or almost sure. So if we minimize it over the gamma and then the B and case, then we will have the B being represented in this form. It's like weighted, we are weighting the ZJs by the function M tau. And then the estimator, whether we obtain, we are calling it gamma, and it is obtained by minimizing the loss function over gamma. Now, if you check this carefully, it's a function of the normalized weight. Here, if you look at the summation here, it's a function of the normalized weight, not necessarily the weight itself, but the normalized one. So this is telling us that even if you start with something that is not one, in the estimator itself, we are going to get something that normalizes. And the theta, don't forget, we have assumed that the theta is independent and then identically distributed, and is independent of the data itself. Now, if you, the first thing we have to do is we have to look at the sum of the weights. Now, if we use the Kolmogorov strong law of large numbers, we can estimate the sum of the weight to be approximately k times phi k of q. If you use the Kolmogorov strong law of large numbers, you obtain that. So this here is telling me that the weight will behave asymptotically of the normalized weight will behave asymptotically as 11. So because we have introduced a theta, we need to get rid of the theta, or we need to have something that is independent of the data we started with. So if we take expectation over all theta. In fact, the results for this one was, or this estimator was proposed by Okran and in his PhD thesis, and it has been published in the second one is in the Journal of Mathematics, or Journal of Mathematics in that way, and then the other one has been accepted for, the first one has been accepted for publication. And if you check it in the paper, it shows that it is unbiased, symptotically unbiased, and consistent. Now, if we take the case where our delta is 0, meaning the alpha is going to 0, then in fact, in that case, he showed that our estimator is, and then here, don't note that the kernel is 1 throughout on the values of 0 and 1. It showed that the estimator is asymptotically normal with mean 0 and variance gamma, 4 gamma squared over 3. And you found out that this is bigger than the variance of the known Hill. The Hill estimator is normal with mean 0 and variance gamma squared. So we tried further to improve it. Again, in his thesis, he tried to improve it. And in the case where we have delta here, And then you show that, in fact, if in this case, because we are controlling how the top, the big values are taken out of the computation of the estimator, we manage to get the optimal variant of gamma square. Okay. Again, here the kernel, we take it to be 1 throughout the space of 0 and 1. Now, the main problem of this one is that, in fact, in terms of application, it is a bit complicated because you may have to generate the estimator for several theta, and then at the end you need to average over the possible theta. So there was the need to do further calculations. So another student of mine, Ajay, Ames Ghana, for him, we proposed estimating the theta. So we take the theta to be the CDF evaluated at the data Z. And then we estimate the CDF by the empirical CDF. Then we evaluate it at the data point. And in that, again, the kernel, we are taking it to be 1 for all values between 0 and 1 here. Then, in fact, in that paper, if these conditions are fulfilled, we show that the estimator will be asymptotically normal with mean 0 and variance gamma squared. So meaning, in terms of computations, we should know that here, we are no longer taking expectations because the theta is depend on the data. So if you replace the theta by the estimator of the theta, which is the CDF, then we get our estimator, and that estimator converges to normal distributed random variable mean 0 and variance gamma squared. Again, if you look at the application of it, we saw that the EVI estimated from it was not stable. At the end, we found out that it frustrates a lot. And because it is unstable, using it as an estimate can cause a problem. Therefore, we again try to improve it further. Now, by introducing the kernel, what the kernel will be doing is the kernel, again, will control how fast the tail will be decaying. I mean, the CDF is decaying. It's trying to factor that one into the estimation. So here on the kernel, we only assume that number 1, it integrates to 1, and then integral of it against t is 1. And then if we do that, and then we are assuming that here that the penalty term is 0 in this case. Here the penalty term is taken to be a 0. Then again, we show that the estimator that we obtain. So note here that we are using the CDF as an estimator, the empirical CDF as an estimator of the theta, then also we are choosing a kernel in it, but the only thing is that there's no penalty term here involved. Again, we show that the estimator, or we normalize it this way, it converges to the normal distribution with mean 0 and the variance gamma squared, integral the kernel square, integral of the kernel square. In fact, this one is good because if we want to achieve the hill, we just have to choose our kernel in such a way that integral of the kernel square will be 1. Then we are in the same situation. And also, in terms of application-wise, we can regulate it in such a way that we can also choose the kernel in such a way that it's the integral of the kernel square will approach 1, will be approaching 1, or will be something close to 1. Then we get a nice, or we get a stable EVI estimate, and then also we get a variant that is comparable to the hill. So the last lesson we did was to now incorporate the penalty term in the previous work. That is, we say that we are saying that in the the weighted least square, the penalty term is no longer 0. Then in that case, if the kernel, if all these conditions here are fulfilled and the kernel integrate to 1, then again, we show that it converges in distribution to the mean, a random variable, which is the mean, with a mean 0 and variance sigma square time, the integral of the kernel square over 0. In fact, this is a good lesson for us because even if we penalize, this is telling us that we are confirming, the result is confirming the case of the unpenalized. Usually when we penalize, we usually call the estimator regularized estimate, regularized. Okay, so the main idea of the proof of the results. First, we estimated from the least square method that the estimator is represented by gamma of this form, and it's a function of the penalty factor, the kernel, and then the rho, which determine the distribution as the type of distribution you have, the stream value distribution you have. Here we are dealing with parity. That is the rho is less than 0. Now we observe that the sum of the weights converges or is asymptotically equal to the sum of the weight we started with, the normalized weight, sorry, sum of the normalized weight is equal to the weight we started with divided by 1 over k times 5 k q. You know, we define it on the previous slides. And this is confirmed, this is by the Kolmogorov-Strong law of large number. So this convergence here is almost sure. Don't forget that in terms of the asymptotic properties, such of the asymptotic distribution of our estimator, we are establishing convergence in distribution. So convergence in almost sure or is stronger. So once we have that, we can all the time apply it when we are doing our convergence distribution. And then also we know that if you evaluate any CDF, continuous CDF at the data point, then whatever random variable you have will be also IID and it will be uniformly distributed over 0 and 1. And then also we also know that if the CDF, the empirical CDF converges to the CDF almost surely, and this is by the Glavinko-Canteles lemma. And then also when we say the rho hat converges to P in probability, we just confirm it consistency. We say it is consistent, estimator. And then also we just have to also show that the penalty term converges to 0 almost surely. And once we know, once these 5 properties are fulfilled, then if the BN hat is going to 0 in probability, then we can also show that the estimator will behave like another estimator, which we are calling gamma hat. Sorry, gamma H. And it is defined as, if you look at this one carefully, it's just weighting the data, the log spacing values by the kernel, okay, and then you are averaging it over all possible top order statistics. So to do this, we first state a lemma that will help us do that. Now we have to observe that by the properties or condition we have imposed on the weight, we can write the BNK as another function beta plus a term that is converging to 0 almost surely. And if it's, and then the BNK is defined as that. You see that there it does not contain anything involving the CDF. It is strictly the kernel and then the data points. So it is a good thing to do. Once we are able to establish asymptotics of the BNKs, then we know much about the beta NKs, then we know much about it. Okay. Again, because of the previous lemma, we can also write our estimator, our proposed estimator, as also a function, as we were indicated, the function I wanted to establish convergence to. We can write it as a function of that plus a term, an error term that is also going to zero very fast on exponential scale. And the gamma HK is given by something like that. And don't forget that if the BNK is converges to zero in probability, then definitely you find out that this will be behaving like what we wanted to show. Yes. Sorry, the YJ here is a capital Y, please. Again, the penalty term will converge to zero. And this can be obtained when you calculate the asymptotic mean square error and you optimize it over all possible values of asymptotic mean square error of the proposed estimator, and you optimize it over all possible values of gamma, tau, and then you find out that you can find the penalty factor, and we will show that in fact it converges to zero. And again, if we have this condition on our proposed estimator for the rule, then again we can establish that with the condition that the penalty factor is going to zero, we can show that the bias, the estimator is asymptotically unbiased as well. Again, we do this through our generated gamma hat, which is a function. We know the gamma is a function of gamma hat plus an error term. So once we do that, before we proceed, we look at these definitions here. So we are calling this term here x1 q rho, and then this term, whenever we see this, we write it as such. And then whenever we see this term, the third one, we also write it as s1 dot, and then in that form, in that manner. In fact, we will learn that our asymptotic mean square error can be expressed in terms of these functions that are defined. In fact, we can express the estimator, our H gamma hat, which is which is an estimator when we add that error term to, or this error term here to, it will give us our proposed estimator. In fact, you can show that the expected value of it is expressible as that, as the functions we have defined. And if you take the limit as k goes to infinity, you will find out that if this term is going to zero and our what do you call it? The penalty factor is also going to zero. Then in this year, if you approximate this by an integration, and this just integrates, it's the integral of the kernel to from 0 to 1, and it is 1. And if we put that inside, we find out all the part will drop here, and then this part here will just also drop in that order. Yes. If you do that, you find out that it will just remain gamma here. It will remain gamma. This part will drop, this part will drop, and then it will remain gamma, because this is also an integral of the kernel over all the possible values, and it is also 1. So clearly, the estimator is asymptotic by scalar. In fact, you can show that the bias term is a function of our BNK and the x1 we define, and then the penalty term of this form. And if the penalty term is going to 0, then clearly this is also going to 0. In fact, the BNK is also going to 0 in probability. Yes, yes, yes. Okay, so our next lemma shows that if this holds, then our BNK, which is the original BNK, not, the BNK here is a function of the beta NK plus an error term. We can show that with the previous lemmas, we can show that this here converges to 0 in probability terms. And then also we can show that asymptotic terms. The asymptotic mean square error is also convert to 0. In fact, yes.
You just have two minutes left, sir. So
okay.
Yeah, thank you.
Thank you very much. So you can also, the estimates on this, the S's are given as follows. And you can use what we call large deviation techniques to show that the BNK converges to 0. And with that, we can calculate the variance of the estimator like that, and you find out that it's a function of the xii, s dot dot, and the s dot dot will convert to 0, and the s dot will also convert to 0. So at the end, you end up having the variance as a function of that party, only this party. And if you put the two together, you can then calculate asymptotic mean square error, and clearly it converges to 0 here, as you see. And then if you minimize the asymptotic mean square error over the tau, you have your penalty term, and you can then estimate your beta. And if you, the way it is, these also go to 0, because anything, the s dot dot and s dot goes to 0. So everything there goes to 0. And I did some small simulations, and we compare it with the previous, right? The hill, the regression, and our own is the weighted least square, the WLX, and then WLXF, and then RWX. In fact, if you look at this carefully, the application, sorry, we apply it to a data from a SOA, and you find out that our own is the, is it a 2? Or yes, you find out our own is doing what is quite stable, a bit stable, but the only problem is the variance is big. So if you introduce the kernel, sorry, here is the case where the data is 1, it is unstable, and you have the CDF inside. So you see that it is quite unstable here, okay? So if you introduce the kernel, let's say this kernel here, then you find out that the same estimator is a bit stable, and therefore is doing well. And again, also when you take even the 1, which was worse in the case of the estimator of the CDF, this is more stable, and you can also see it. In conclusion, we have achieved our result. We have the estimator, and then it is asymptotically normal with mean 0 and variance sigma squared, and it is comparable to the hill. These are some references. I think I'll end here. Thank you very much. I hope.
Thank you, sir. Thank you very much. All right, we don't have time for questions. So the next speaker is Tolo. Tolo is from the University of Illinois in the United States. She was previously a lecturer at the University of Essex in the UK. Tolo, can you hear us?
Yes. Can you hear me?
Yes, sure, we
Great.
can hear.
So I'll just share my screen. Okay. Oh. Yes. So let me know when you want me to start.
Okay, you can start now, Tolo.
All right. Okay. Thank you very much. Also, first of all, I would like to thank the organizer for putting together this workshop. Thank you. So this morning, okay, so good morning, good afternoon, depending on where you are. And this morning, we talk on optimal reinsurance with multiple risk and dependence on uncertainty. And this is a joint work with my colleague when I was at SS, Julie Hu and Peng Liu, and UC, one of their PhD students. So for example, let's assume that we have a homeowner that lives in California in an area that has a history of wildfire, or a homeowner that lives in KwaZulu-Natal in South Africa in an area that has a history of flood, or a homeowner that lives in Adamawa State, Nigeria, in an area that has a history of flood. And this homeowner wants to purchase insurance contracts just to protect he or herself in the event of, let's say, wildfire or flood. And let's say the claim is like $200,000. And this individual approached an insurance company. And then the insurance company takes over this contract, but they don't want to cover or take over the entire risk of paying $200,000 in the event of wildfire or flood. And then the insurance company decides to approach a reinsurance company, and then just to say, okay, I want to transfer. I have this risk of paying this individual $200,000 in the event of flood or wildfire, but then I don't want to cover the entire loss. But then I want to transfer some of this risk to you, such that in the event of wildfire or loss, then if we have to pay this individual $200,000, then the insurance company will pay part, and then this reinsurance company will pay part. And then the question here is, what is the optimal reinsurance contract that will minimize the risk exposure of the insurer? In other words, what is the percentage of this $200,000 that this insurance company should transfer to the reinsurance company to cover? But in my talk today, I'm going to introduce a framework that is much more complicated than what I just described, in the sense that we are going to consider insurance company with multiple lines of business. So when I say multiple line of business, I mean, so the example I gave is just homeowner insurance, but this insurance company, they have homeowner insurance, car insurance, health insurance, life insurance, and then this insurance companies still want to purchase reinsurance contracts for each line of business. So in my talk today, I will introduce an optimal reinsurance design from the perspective of an insurer with multiple lines of business that want to purchase reinsurance strategy contract for each line of business. And then for the risk vector that is being generated by this line of business, we are going to assume that we know the marginal distribution, but we do not know the dependent structure. So, and the fact that we do not know the dependent structure, we end up investigating something like a worst case scenario. And then we want to find the optimal reinsurance strategy for each line of business that this insurance company actually holds. So reinsurance is like an insurance that insurance company actually purchases, but not only to reduce their risk exposure, but for other purposes. But in my talk today, we are going to study variance value at risk, and then range value at risk optimal reinsurance problem for worst case scenario under dependence uncertainty. That is, we want to consider the dependent structure that gives rise to the largest level of risk for any reinsurance contract. And the result I'll be presented today will be based on robust risk aggregation. So why reinsurance? Recently, Swiss Re, that is Swiss Reinsurance, actually they presented a global premium volume for 2015. And then they said that for life and health insurance, so life and health insurance are like endowment, your regular health insurance, and non-life insurance would be maybe business insurance, car insurance, homeowner insurance, funeral insurance. So those are the non-life insurance. So now for primary insurance, which is more like your normal primary insurance, like Allianz, Old Mutuals, so they said that life and health insurance account for over 2 trillion, and then non-life insurance for like 2 trillion. But then for reinsurance, they have, for life and health insurance, they have $65 billion. And then for non-life insurance, they have 170 billion. So for reinsured risk, we can see immediately that the volume is small, right, compared to insured risk. But reinsured risk, they're actually they are more complicated to handle compared to insured risk, because they tend to cover extreme events, like the example I gave earlier, like wildfire, flood, natural disaster that are less to predict. And when it happens, the claims are always kind of huge. And then what are the benefits of reinsurance for insurance company? So it helps the insurance company to reduce their risk exposure because they don't want to take on all these huge risks, and then they transfer some of them to the reinsurance to deal with. And then it also helps insurance company to underwrite more insurance contract because if they transfer most of their risk, then, or if they transfer their risks that are really, really risky, then they can then take, more, they can take on more contracts. So like I said earlier, I'm going to be talking about multiple risk, whereby insurance company has multiple line of business. But before I will go into that, I will introduce a single risk framework. So here, an insurance company faces a risk X. So this could be homeowner insurance or any type of insurance, but a single insurance over a period. And then F of X here now is that part of the X that the insurer decides to, transfer to the reinsurer. So when the insurance company transfers for first to the reinsurance company, then they are going to be left with this retained loss, which will just be the risk, then minus what they transfer to the reinsurer. So they will be left with this, which we call the retained loss. Now, for the insurance to transfer their risk, this F of X to the reinsurance company, they have to pay something as premium, and that is this pi. Now, the total risk exposure of the insurance company now is going to be the risk that is left, which is a retained loss, and then what they pay as premium. And the question here, or the task here, is that we want to find the optimal reinsurance strategy, which is more like the optimal F, right? That is the ceded loss function that will minimize the total risk exposure of the insurer or the insurance company. So now this pi here is the risk measure. So you could use any risk measure of your choice. And then pi here is the premium, which is the amount that the insurance company paid the reinsurer for taking on this risk. And this F here is the ceded loss function, which is the risk that has been transferred from the insurer to the reinsurer. And then so for the risk measure, you can use, like I said, your favorite risk measure, expectation, standard deviation, depending on you. But here we have the value at risk, expected shortfall, the range value at risk, which is kind of seen as the limiting the expected shortfall and the value at risk, they are seen as the limiting case of the range value at risk. And we have the other risk measure like coherent risk measure, converse risk measure. But in my talk today, I'll be using value at risk, which basically measure the potential loss in a portfolio at a particular time and at a confidence, given confidence level. And then for the premium principle, one can use different type of principle. We have the expectation principle, which is denoted as this, and then the standard deviation, the Wang principle. But in my talk, I'll be using the expectation principle to compute the premium. Okay, so now for the loss function. So we have two loss function, the ceded loss function F, which is the risk that is transferred from the insurer to the reinsurer. And then we have the retained loss, which is the risk that is left, right, with the insurance company. And then we assume that both the ceded loss function and the retained loss function, they are non-negative and they are increasing, which basically implies that their Lipschitz continues. And this property is very important because it basically ensures that as risk increases, then the risk shared by the insurer and the reinsurer also increase just to avoid moral hazard. And then for the ceded loss function, we have different type of ceded loss function, the quota share, the stop loss. So this quota share now, a good example of the quota share would be, so like the example I gave earlier, so the claim would be like $200,000. So quota shared would be a percentage would be transferred to the reinsurer. So because here A is just between 0 and 1. But we have other type of ceded loss function, which I will introduce some of them along in this talk. Okay, so now this is the multiple risk, which is where our interest lies. So here, the insurance company usually have many lines of businesses. So think of Old Mutuals or Allianz. They have health insurance, life insurance, car insurance. They have all this in their portfolio. And now they want to put, this insurance company wants to purchase reinsurance contract for each line of business. So in this case, since we are considering more than one risk, the SF here would be just the total risk exposure of the insurer after purchasing a reinsurance contract for each line of business, right? Because FFX is the transferred risk, and this pi high is the premium that insurance company pays the reinsurer. And again, we want to find the optimal reinsurance strategy that minimizes the risk exposure of the insurer. But then in many cases, individual risks are not completely independent. So for example, if we look at the case of COVID, so during COVID, the impact of COVID was not only felt in, say, the health sector, or I mean, like in health insurance or life insurance, but also business insurance, because when we had COVID, there were a lot of claims on health and life insurance, and then also claims on business insurance due to the global shutdown. But then on the flip side, when one look at car insurance during COVID, there were minimal, I mean, the claims there actually reduced because we had lockdown and then we're all working from home, so which means there were less cars on the road. And then social gathering was restricted, which means there were less drunk driver on the road, which means there were less accidents on the road. So when we look at car insurance and car claims during COVID, that kind of reduced. But then when you come to the side of health and life insurance, then the claims they increase. So then we can see some kind of dependent structure on these lines of business that they kind of depend. I mean, there's a kind of underlying dependent structure on them, but it's difficult to quantify this dependent structure. And that is why in my talk today, we assume that we have uncertainty of the dependent structure. So we do not know exactly what the dependency looks like, but we know that they are kind of correlated in a way. But then now we want to find the optimal reinsurance strategy for each line of business, even though we do not understand the dependent structure of these lines of business. So there are a few papers in the literature that actually study something similar, but not exactly the same as ours, because this paper by Carl Wee that was published in IME basically assumed positive dependence through stochastic ordering on the risk. And then the paper by Chong Song and Yam, kind of similar to what we did, because in their paper as well, they assumed that the dependence structure is unknown. But for their risk measure, they consider converse risk measure, which is more like a special case of our own results. And then it turns out that the risk are comonotonic, which means they have positive dependence. And for their premium principle, they use expectation type, which is expectation principle. But so in our paper, we kind of use general, let's say, risk measure, because we consider converse risk measure and non-converse risk measure, right? And then we are able to find the optimal reinsurance strategy for each line of business. So now this is what my model uncertainty framework looks like. So in practice, it is difficult to know the dependent structure, like I argued earlier. And then now we define our uncertainty set as this A. And then we consider the worst case scenario, meaning that we want to consider the dependent structure that gives rise to the largest risk exposure for the insurance company. And then we want to find the optimal reinsurance strategy for each line of business that minimizes the risk exposure of the insurer. Now, the set DN here is actually the set of seeded loss function in this case. And then we have this constraint. So this constraint basically means that this is summation of all the premiums, right, that has been paid, which basically means that the total premium paid by the insurer to the reinsurer should be less than their budget. So which means, I mean, they cannot pay more than what they actually have in their budget to cover this particular risk. And this is what this constraint is actually telling us. So now, a few properties on the premium principle. So we assume that our premium principle has distribution invariance, which means if I have Y and Z and they have the same distribution, then the premium on Y should be the same thing as the premium on Z. And then I have this risk loading, which tells that the premium on Y should be more than the expected loss. And then the reserving the stop loss order, which says if Y is less than Z in stop loss order, then the risk, the premium paid on Y should be less than that of Z. And we have this continuity property that we use to establish the existence of the optimal reinsurance strategy. So now for our results, when we use value at risk, for our risk measure, and we consider two risks. So two risks basically means this insurance company has just two risks, maybe car insurance and homeowner insurance, or health insurance and homeowner insurance. And then it turns out that the limited stop loss policy is the optimal reinsurance strategy. So this is an example of what the limited stop loss policy looks like. So this is the formula. So here, if we assume that A, which is what we have here, is 2 and B is 4, this is what the seeded loss function looks like, which means that, so if X is our risk, you can think of this risk in terms of any figure, maybe billions or dollars or millions. And then you say that for risks that are less than 2, the reinsurer is going to pay 0. So that means they're not going to cover it. And for risk between 2 and 4, then the reinsurance companies are going to cover it. And for risks that are more than 4, it's being capped at this level. And then we are going to define this set of A as a set of parameters such that the limited stop loss function is actually in this is in D, which is a set of seeded loss function. So yeah, so this is our first result where when we consider 2 risks, and then we use value at risk as our risk measure. And then so we suppose that the contours are continuous. And this is what our optimization problem looks like. So this is the worst case value at risk for the risk aggregation. And then this is more like our minimization, whereby we want to find the optimal seeded loss function for F1 and F2 that minimizes the risk exposure of the insurer. So we show that this representation here can be written as this representation here. So for the proof of this, the first one is basically based on the inner one. So this is more like a 2 layers optimization problem. So the inner one, which is a worst case type, we show that this worst case equation here or representation here can actually be written as this if convolution formula. And then we show that this set of seeded loss function can actually be written as a set of parameters such that F is in D. And then so we show that the optimal reinsurance strategy here is the limited stop loss policy, provided that this had the optimal parameter. So that is the case for when n equals to 2. So, but when n is more than 2, then things becomes much more complicated to handle. So in that case, we first of all extend the result in Blanchard, Lam, Liu, Wang in 2023, which is this year. So we extended their results to the case. So in their result, they have this representation, which is the worst case value at risk. That there is same thing as this if convolution, but they have this result for marginals that have decreasing densities and increasing densities. So we extended their result to marginals that are convex and beyond their quanta, alpha quanta, and that are and to marginals that are concave beyond their alpha quanta. So we established that this representation holds, and this is what we are going to use. And one of the reasons why we cannot use their result for decreasing marginals or increasing marginals is because if I have risk X that has decreasing density, the minimum of X and A may not have decreasing density. So we extended their results and we say that this holds for convex marginals with convex tails and for marginals with concave tails. So for the first result, which is for marginals that have convex distribution on their tail part. So, and for this to hold, we assume that the seeded loss function here is convex, and this is what an example of seeded loss function that is convex, what this looks like. So this is similar to, this is for general stop loss policy. And this is more like a piecewise linear function of 3 cases, which is so for the first part again, when our risk is less than 2, these are not covered. And then for risk between 2 and 4, then 100% of C is covered, 100% is covered. And for C that are more than risks that are more than 4, the 100 plus the percent of it has been covered. So this is the result for when we have convex marginals with convex tail distribution, very similar to the case where we have 2 risks, but here the number of risks is more than 2. So that is the beauty of this result. And then again, we show that this representation here can actually be written as this, and then the optimal reinsurance strategy is going to be something that is convex in nature, and we show that these are the optimal parameter. So we did the same thing for the convex and concave distribution on tail. So I will skip this for the sake of time. And this is our result. So that is the result when we use value at risk for our risk measure. And then we have results when we use range value at trace for our risk measure, and even when we use expected shortfall for our risk measure. So we did similar thing in the sense that we extend Blanchard, Lam, and Liu Wang results to the case where we have marginals with concave distribution on their tails, because their result, they have decreasing densities again, but we extended their result to the case with concave distribution in the tape part, and then we are able to find the optimal reinsurance strategy when we use range value at risk as our risk measure, and when we use expected shortfall as our risk measure. But to put my result into perspective, consider the case where n equals to 2. So numerical studies for when we consider two risk. If you remember the theorem that I presented earlier, this is what the theorem looks like, and then this is what our result, right? So this would be the optimization, which is more like two layers optimization problem. So the first thing that we did was we solved for this inner one where T is our control variable, and then we solve for this outer one where A1, A2, and B1 and B2 is our control variable. And for the premium principle, we use expected shortfall for our premium principle. So this function, our optimization problem is a non-convex optimization problem. And so then, it's a non-convex optimization problem, which makes it a bit difficult or tricky to solve, because then we have to find the local optimum in each grid and then find the global optimum T. So that's what we did here, but good news is that our non-convex optimization problem can actually be reduced to a linear minimization problem. So we're able to solve this optimization problem. And then I will just present an example where we consider exponential marginals. So in this case now, x1 and x2, we assume that their distribution is exponential. So they are exponentially distributed. And then for value at risk, we have the formula for value at risk in exponential distribution. So we're able to use the result for the formula for value at risk on the exponential distribution for x1 and x2, and then using the formula for the premium principle. This is what our optimization function actually looks like. This is what our problem looks like. So we have this optimization problem, and then we have more like a closed form expression for health, right? And then we can solve this. So we consider this for exponentials, and then we construct our risk. So we construct x1 and x2, and we construct x1 in such a way that x1 is more risky than x2. How did we do that? So for the x1, the mean is 8,000. Then this theta 1 here, which I didn't mention earlier. So we have this theta 1 in our formula for the premium principle. So I'll just quickly come back. Yeah, it's here. And what it does is the risk loading, which basically tells the riskiness of the risk that the insurance company wants to take on. So if this is bigger, the bigger this is, then the more risky the product is. So in our example, so for x1, we assume that theta 1 is 0.8 and theta 2 is 0.3, which means we construct this risk in such a way that x1 is more risky than x2. And then we solve the optimization problem that I introduced earlier. And then it turns out, so this is more like the solution to the optimization problem for x1, and this is the one for x2. And it turns out that for x1, the optimal reinsurance policy is this limited stop loss function, which means for risks that are less than around this area, then the reinsurance is going to pay 0. They're not going to cover it. And for risks that are in this area, they're going to cover it, but what they are covering is actually capped at this level. And this is value at risk of FX in this example. And then for Y2, this is what we have for Y2, which is the optimal insurance strategy is the stop loss or policy, which means it's not capped. So the insurance company, they are ready to cover all the reinsurance company are ready to cover all the risk at this level. And also we check how the decision of the insurance company changes as their confidence level change. And this is what the result that we presented. So for the sake of time, I will skip this part. So in summary, it turns out that for worst case value at risk and range value at risk-based model, counter monotonicity is the least favorable dependent structure among the insured risk, which means the dependent structure among the insured risk is negative. And then for the case of expected shortfall, the behavior or the least favorable dependent structure is positive, is comonotonic, which means they have positive dependence. So our main result actually shows that finding the optimal seeded loss function for the worst case reassurance model with dependent uncertainty actually boils down to finding the minimizer of a deterministic function. So this paper is available on SSRN rather, and these are a few of the papers that we use. And I would say thank you all for your attention. I'm ready to take questions. I think I have just 1 minute left. So thank you for having me.
Thank you, Tolu. Very, very interesting presentation. Yeah. Any questions for Tolu? Hello. Questions for Tolu? Yes, one person. Yes. You
Yeah,
can...
no, I don't have a question per se, but I think this is just an interesting presentation, Paula, and I would like to ask Queensley to invite her to our research group. I think she will fit and she will contribute to, because I think we are also dealing with some of the aspect that she was talking about when it comes to reinsurance.
Oh, okay.
Yes.
Thank you.
Thank you.
Thank you very
Thank
much.
you. Yeah, yeah.
Yeah, I myself have done some work on insurance. Maybe not to the level Tolu has done, but I published 1 or 2 papers on insurance mathematics and economics. I'm sure you know that journal is called
IMA.
IMA, yeah. And also the Scandinavian Actuarial Journal, which is another journal I published in. So yeah, I mean, I'll be pleased to work with you if we have common interest. I mean, something I'm sure we can work out.
Yeah, true.
Yeah.
Thanks. Yeah.
Thank you very much.
Thank you, Tolu. So let's
and the emails of the participants will be available somewhere, right?
Yes, they are in. You should go to the website. The emails are all on the website of everyone who has given a talk or everyone who agreed to give a talk. Let me paste it here. Let me paste it on the chat room.
Okay, thanks.
Yeah. All right, guys. So let's take a break now for the lunch. I'm sure it's not the lunch time for you guys, but not for everybody. But we will restart in 1 hour time exactly. So it's 2:30 p.m. UK time. Not sure about your time, but it will be exactly 1 hour from now. We will start again. All right. So see you.
Okay. Bye.
Bye. Please,